So you all just worked on this worksheet in your breakout rooms on Zoom, together as a group with those of you who are virtual, but also those who are in class. And what I want to do is just take some time going through each of these questions so that those of you at home can get a chance to double check that you are correct and that you had the right way of thinking or a good approach to these types of problems. So I'm just going to run through the first two pages of this because just as a reminder, you guys were to work on these two pages, and then this final page there is a video for, which is your homework assignment, completing these notes and getting comfortable with linear, quadratic, and exponential. So let me go back to the top and let's start going through this. So it says describe design 7. So we're going to take this design 1, 2, 3 and try to expand it to what it potentially could look like for design 7. Something to note is that it looks like design 1 has just a single square in the middle. Design 2, there's like a 2 by 2 square in the middle, or 4 total. Design 3, I see a 3 by 3 square in the middle, or 9 total. So you got to think about how does that relate. Geometrically, what you can see is that whatever the design number is how big our square is dimensionally. So design 7 is going to be a 7 by 7. 7 by 7 inside, so 49 total. But then notice how there's still these 2 always just kind of hanging out, right? And then there's just going to be 2 on the outside always. So we kind of have an idea of what it could look like. Now, I'm not going to draw all 49 of those squares here, but it's the idea that this is 7, this is 7, 49 total. That doesn't really look like a 4. Let me rewrite that. 49 total. That's kind of what it's looking like. So drawing it out. So how many squares are in it? 49 plus 2, 51. Write an expression. This is where it gets tricky. And this is where I really want us to get better at as we progress through this unit, because it's visualizing it, but also you could use the numbers to get there and look at the pattern in the numbers. Write an algebraic expression to represent the total number of squares in design n. Okay, so whenever you say, oh, it's the design number 3 by 3. Oh, it's the design number multiplied by itself. What you have to do is take that statement and turn it into an expression using not the design number, but you need to use n. Okay, so what I see in this is that there's always these 2 just hanging out. There's always 2 on the outside. So that is a constant plus 2. But what I notice on the inside and how it's changing, design 4 would have a 4 by 4 dimensional square on the middle. So there'd be 16 total. So what's the relationship? Well, whatever the design number is the number in terms of the dimension we have. So if this is design 3, it is 3 by 3. This is design 4, it is 4 by 4. Design n would have n by n. So how could I calculate the squares in that? Multiply it by itself, n squared, right? You could also just look at the relationship. This is design 3, and there are 9. This is design 2, and there are 4. Design 4, and there are 16. So what's the relationship by the numerically numbers? Well, 4 to 16, 3 to 9, 2 to 4, oh, it's just squared. So that's what it's looking at. And the final part, number 5, find how many are in design 52. That would be terrible to count it out, so good thing we have our expression. Plug in 52 for n, square it, and add 2. All right, so that's kind of a thought process we can use. So let's look at the rest of these. Generate an expression to determine the fish, blocks, or apples for design n. So pattern 1, let's see here, there are 2 total, 4 total, 2, 4, 6 total. Well, notice what's happening here. Pattern to total number, pattern to total. It looks like it's being doubled, right? It's twice the value of the pattern. So I could say twice the pattern number, 2n. All right, so that's one way of looking at it. But also notice that this is increasing by a constant value from 2 to 4, 4 to 6. It has a constant increase. That's a concept of like a linear relationship, which is something like this. A linear relationship has just an n. It doesn't have an n squared. So that's one way to see it. All right, let's look at the next one. Pattern 1 has 1. Pattern 2 has 3. 3 has, notice what's happening here. 1, 3. This has 5. The next one has 7. We know the next one would have 9. So we see a pattern. But what's difficult about this one is it's not as simple as 2n. Pattern 3 has to get to a 5. Well, 3 to 5 you could add 2. Yes, but for pattern 4, I need 7 total. I'd have to add 3. Okay, so that means it's not the same rule, and I can't just say n plus 2 or n plus 3 on this one. It doesn't work that way. This rule has to work for every single one, and it has to represent n for the pattern. So if I plugged in pattern number 99, if I plugged 99 into this expression, I should get back the total number of blocks. Okay, so look how they're kind of almost double, like 4 to 7, 3 to 5, it's almost double, 2n. But it's actually 1 less than it. If you double 4, you get to 8, 1 less. You double 3, you get to 6, 1 less. You double 2, you get to 4, 1 less. Right? So that's one way of seeing it. And notice once again, it has a constant value being added from one to the next to get there. That plus 2 told us that it was linear or a constant relationship, so it's 2n there. Okay? Continuing here, let's see what we have here. Pattern 1, let's try to do this one more geometrically, like looking at the shape. We did the first two like trying to count the numbers. Let's take a look at the shape here. So pattern 1 has a set of 3. Pattern 2 has 2 sets of 3. Pattern 3 has 3 sets of 3. Okay, so what could we do with that? There's sets of 3, so it's the pattern number that tells you how many sets. But there's always 3 in that set. All right, so we're kind of thinking about how that expression could be built. I also notice that there is just a plus 2, or sorry, there's just 1 added here and 1 added here at all times. That's a constant value. So I know my expression is going to have a plus 2 at the end because that is constant. Okay? Now, you guys probably worked through this. You're thinking about how could this work. Let's also look at it in terms of the numbers. This one has, pattern 1 has 3 there. Pattern 2 has 6 in the middle. Pattern 3 has 9 in the middle. So what's happening here? It's the pattern number multiplied by 3. 2 to 6, 3 to 9, 3n. Let's confirm it though. Let's make sure. All right, 3 times the pattern number. So pattern 2, let's plug it in. Plug in a 2 right there. 3 times 2 is 6, plus 2 is 8. There are 1, 2, 3, 4, 5, 6, 7, 8. We know we have it right. All right, so that's a tricky one, but it's a different way to look at it. Try to see it visually or just count it up with the numbers. Pattern 1, this one should be pretty straightforward. There's 5 total. 2, and this is a set of 5, right? Pattern 2 has 10 total. Pattern 3 has 15 total. Well, what's the relationship here? It's a constant 5 being added every time, right? So we can see that. So if it's plus 5, it's going to be a 5n. 5 added from one to the next. So it's linear. It's a constant relationship. And from 1 to 5, you multiply by 5. From 2 to 10, multiply by 5. 3 to 15, multiply by 5. Okay, let's move to the next one. Gotta make sure we go quick through this so I don't go over my time limit, which I like to keep under 15 minutes for these videos. So this determine the number of squares in the next 2 patio designs of the pattern. So we can kind of see what's happening here. Design 2 has a 2 by 2 square. Design 3 has a 3 by 3 square. Design 4 would have a 4 by 4 square. But notice what else is happening. Design 2 has 2 here, 2 here. Design 3 has 3 here, 3 here. Design 4 would have 4 here, 4 there. So we're trying to see the relationship, but also relate it to design number. Remember, n is the design number. So design 3 has a 3 by 3, which is 9. Look at the relationship. It's squared. 4 by 4, which is 16. It's squared. That's that concept. I'm kind of skipping ahead here for a second. Design n. Find the expression, total number. Look at what we see here. 2. This is a 2 by 2. There's 4. That's squared. N squared. But it's not just that. Notice design 2 has a set of 2 and a set of 2. So it's an n, and an n. Design 3 has a set of 3 and another set of 3. So it's plus n, and yes, you could definitely call this 2n. Okay? And the last one, notice there's also these hanging out here at each time. These are a constant plus 2. So n squared plus 2n plus 2. And real quick, I do want to show one other way to do this one. I'm going to run through it quickly, but I do want to show a different geometric way to do it, and they are going to be equivalent. Right? The answer I get may not be the only correct answer because of distribution could allow us to get there. Design 3, let's actually not do squares, let's do rectangles. This is going to be an interesting one. Look what we have here. Design 3 has a 3, which is n, by 1, 2, 3, 4, 5. Well, that's 2 more than n, 2 more than n plus 2. Okay, so we're looking at not squares, but we're looking at rectangles. Let's see what this one, let's see if this holds true, if it has that same relationship. Design 2 has 2, which is n, and 2 more than it, n plus 2. So this could be pretty cool. Let's see. If we're going to do a rectangle, it's not n squared, but it's n times something, right? So it's n times n plus 2. But don't forget about these 2 that are still hanging out here and here. So what we have to do is distribute. And we get to confirm that these are the same. Let's see. N squared plus 2n, when I distribute here, plus 2. So instead of thinking about it as a square, we thought about it as a rectangle, and we related it to the design number in order to get there. So that's why, this one, if we were to try to do it just with the numbers, like count up all the squares, it would be really difficult. But if you can see it geometrically in the pattern, it's a lot easier. And the last one, I'll be quick on this, design, and hopefully you guys were good with this one. Design 4, notice there is a 4 by 4. Design 3, there is a 3 by 3. What does that mean? N squared. What do we have here? Design 4 has 1 set of 4, 2 sets of 4, 3 sets of 4, 4 sets of 4. N's, those are all N's. That's N, 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 N. Design 3 has 1 set of 3, N, another set of 3, another set of 3, and another set of 3. N, 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 add them up, 4N. That's our expression for this last one, right? And there's more that could have been asked for a couple other ways to do it. You could have once again made a rectangle and done this. And then you would have seen it's the same thing. You got design 2. It is a 2 by 4. And then there's just 2 hanging out, right? Design 3, it is a 3 by 5. So it could have done a rectangle as well. That's it for this video. Homework assignment, make sure you just watch that next video in preparation for next class.